Lots of announcements. Share my screen. Okay, so we are going to be in chapter 4. Where is it? There it is. Share screen. Okay, chapter 4, here we go. So I'm going to pull the chat back up so that I can see questions as we go. We're going to have several poll questions today, so be paying attention because I'm going to try to kind of quiz you and review you as we go, which helps everybody, I think. And we have a lot to cover. So first, a fun hiking picture though. So this is a hike that my husband and I did before we had kids. And I was actually pregnant with our first kiddo, our daughter, on this hike. So we don't get to go do hikes as freely as we want anymore. But this is in Tennessee. Sorry, the text down here is kind of dark, but it's called Cummins Falls. And we went to Nashville, Tennessee for a trip. If you've ever been to Nashville, it's such a great city to go to. If you haven't, you definitely need to go vacation there. Except for the fact that they got hit by a tornado like earlier this year. That's another crazy thing in 2020. But they're recovering. Anyways, there's lots of great hiking around Nashville. So it's a great city. And then if you like to hike, there's a lot of that. It's all in one, city and hiking. So at the end of Cummins Falls, you hike down kind of into this crevice, and then you hike along this creek, whatever you want to call it. It's kind of big for a creek. And you get to Cummins Falls, and it's a very popular place for people come swim. And you see it's kind of flat in there. So people can very carefully walk up in there. And if you're wondering how big this is, my husband decided to go for a swim. So there he is in the bottom of the picture. And it's ginormous, okay? It's bigger than it looks. But this was beautiful. It was one of our favorite hikes that we did while we were there. We did this in March, so it was extremely cold. So I said, you have fun. I'm going to take pictures. But Cummins Falls, highly recommend it if you ever go to Nashville. And if you're wondering, I will get to some Arkansas hikes, but I'm saving those for later. Okay, bonds, chapter 4. So hopefully you are keeping up with the textbook reading. There was about 4 or 5 sections of the textbook reading to do. Covalent bonds are the second type of bond that we are talking about. We've already talked about one whole ballpark of bonds, right? That's ionic bonds. And covalent bonds are the other kind of bonds. So how did we say covalent bonds are different than ionic bonds? Well, it is a bond formed by the sharing of electrons. So we are no longer, get it out of your head, what happens in an ionic bond. In an ionic bond, you have one atom, and it completely trades an electron to another atom. So one atom loses, and the other atom gains an electron. And therefore, you have 2 ions, and they're bonded together via that trade-off of electrons. But we're not trading electrons here. We're just sharing them today, okay? All right, so let's talk about this. Molecular compounds. These, we call things that form covalent bonds, we call them molecules. Or we don't call them ionic compounds. We don't call them crystalline solids. That's ionic bonds. Things that are formed by covalent bonds, we call those molecules or molecular compounds, okay? So there's some terminology differences to be aware of here, and so some vocabulary to become used to. Molecules, molecular compounds, these are things formed by covalent bonds, and these usually form between 2 nonmetals. Okay, remember with ionic compounds, you had a metal cation and you had a non-metal anion. All right, but here we have 2 nonmetals. So I put a picture of the periodic table because we need to remember, okay, where are our nonmetals? Let's look at that. Anything in blue, all right, and some of the purple stuff. These are the things that more generally form our covalent compounds, all right? So we will not see any of these metals in molecular compounds, in covalently bonded molecules. So we're shrinking down our periodic table, and the elements that we're talking about today and dealing with for today and next Tuesday, it's a very small realm, okay? It's just nonmetals. All right, now let's fill out this other part, because when we talk about covalent bonds, I want it, there we go, nope, sorry. Having fits here, whatever. Now, one thing that is similar, we are still abiding by the, guess what, octet rule. All right, so don't forget that. The octet rule says that we want to stabilize atoms by having them achieve a full set of valence electrons, a full set of 8, that is. So the goal of electron sharing even is to stabilize atoms, again, by achieving a full set of valence electrons, and that is 8 in the outer shell. So we're still abiding by that rule, and that rule of 8 is going to help us figure out how many bonds different elements and different atoms are going to form in a molecule. Now here's what's happening. Here's two pictures, or a picture of two atoms approaching one another. Okay, so we have atom number 1 on the left, atom number 2 over here on the right. And as atoms get close together, you have two things at play. You have attractive forces and repulsive forces, and that's what you see with the arrows. The blue arrows are the attractive forces. Guess what? That is between the electron cloud of one atom and the nucleus. I'm just going to the nucleus of another atom. Okay, those things are attracted. Why? Because remember, the nucleus is positively charged and that electron is negatively charged. All right, and then same thing down here. We have an electron cloud. The atom on the right is attracted to the nucleus of the atom on the left. So you have those attractive forces, but you also have repulsive forces. Okay, repulsive forces between the two nuclei, and that is this is the bigger arrow. Okay, on the bottom, that's showing you the repulsion between the two positively charged nuclei of each atom. And you have repulsion between the two electron clouds. So why does a covalent bond form? How does it work? How do we share electrons? Well, it works because the attractive forces are stronger than the repulsive forces. Okay, that's the only way we could get a bond. It's just that the attractive forces are stronger than the repulsive forces, and that's how covalent bonds, that's how they work. All right, I'm going to give you some phrases today that I'm going to encourage you to memorize, and that will help you with what we're going to be talking about. But here's one thing that's really critical is in this red text that we're about to fill out. Anytime electrons are shared, you need to know that both atoms in the bond, okay, because a bond is formed between two atoms. Both atoms in the bond claim all the shared electrons. Both atoms in the bond claim all the shared electrons. That's going to be important as we count electrons, okay, to get the 8, to get the octet. We need to know that. So for example, let's look at a molecule of hydrogen. All right, hydrogen is a nonmetal. We have two atoms of hydrogen approaching one another, and over here they have formed a molecule. Now, remember, hydrogen and helium are an exception to the octet rule. Okay, so they're full when they get 2 in their outer shell because they only have one outer shell, one circle around the nucleus, one energy shell. And we have one electron in each of those, and when they come together and they share those electrons, we indicate that, or we draw a picture of that by putting the 2 electrons right here in the middle between the 2 atoms. That is what we indicate as a covalent bond. There's other ways to represent that. I'll show you in just a second. But they both, this hydrogen atom on the right and this hydrogen atom on the left, they both claim those electrons because they're fully sharing them. They both now C2, and they both claim 2 electrons, and they're full, okay? Now, with elements beyond helium, lithium, and so on and so forth, everybody wants 8. But with hydrogen and helium, they're full when they have 2. Remember that. So other ways we can demonstrate a bond here, not just what looks like a colon, those 2 electrons, 2 dots. You can also indicate a bond with a line or a dash. In fact, this is how we're going to do it with Lewis structures. We're going to learn how to draw Lewis structures today. If you've heard of that, it's a lot of dashes, okay, a lot of lines connecting different elements. Or we could indicate that this is a molecule of hydrogen by just writing H2, okay? That indicates that there's 2 atoms bonded together, which is what we see here in this picture, one hydrogen molecule. Or you can draw the electrons out like this, okay? Most commonly, we're going to use a dash, a line. And you need to remember that a line connecting 2 atoms indicates how many electrons? 2. There's 2 electrons in that bond, okay? Simple math. So bonds are represented with 2 dots or a, why did I put 2 blanks? Or a dash, okay, or a line. I don't know why I put 2, I don't remember what I was going to say there, but a line or a dash, that's how you can also represent the 2 electrons. Okay, here's another example with chlorine, okay, down here on the bottom. So don't forget about electron dot structures. We've got 2 chlorine atoms right here, and we're showing the number of valence electrons they have. Okay, there's 7 electrons around each of these, all right? Now, the one that's red is the one that is unpaired, right? Everybody else is paired up, but the unpaired electron on each chlorine, these, when the 2 chlorine atoms come together, those are the electrons that they're going to agree to share. Now, let's count how many does each chlorine atom claim to have, okay? So let's look at the chlorine on the left, right here. We've got 1, 2, 3, 4, 5, 6, and if it claims both in the middle, that's 8. So this chlorine atom claims all of these. Well, guess what? The chlorine atom on the right, it also claims those 2 in the middle. And when you count those up, now each chlorine technically has 8. Okay, that's how this works. Here's just kind of another picture. We didn't go into electron configurations, and so these green looking shapes don't matter to us, but I just want you to see we've got these 2 unpaired electrons, and then they pair up in the middle, and that's our covalent bond. Let's talk about diatomics really quick. So what is a diatomic? Well, these are covalently bonded atoms, and this is how they exist in nature. All right, it's elements that naturally exist as 2 bonded atoms. There's 7 of these, okay? And you need to memorize. You need to memorize these 7. And there's really, it's just kind of rote memorization here. The only trick I can point out to you is that if you look at the periodic table, they form a 7, except hydrogen here. See, here's our 7. There's 7 elements that exist as diatomics, and 6 of the 7 form a figure 7 on the periodic table, then plus hydrogen. So you've got nitrogen, oxygen, and then your halogens: fluorine, chlorine, bromine, iodine. They exist exactly how they are drawn here, N2, O2, F2. When we write these elements, and hydrogen, don't forget hydrogen as well, we're going to write them with a 2. So what we're not going to do, we do not write diatomics as a single atom. It's not correct. Anytime you write a chemical reaction, which guess what, after we finish chapter 4, we're going to get into chemical reactions in chapter 5. Anytime you write any of these diatomic elements, you cannot just write them as a single element. I cannot write hydrogen just H. It doesn't exist that way. When it's by itself, this is incorrect. We have to write it as H2. Okay, oxygen, same thing. You're never going to see me write O by itself. If it's by itself in a chemical reaction, it's O2. And that rule applies for these diatomics, and only the diatomics, okay? It does not apply for elements like, for example, sodium. You would write sodium just a single atom. It's not a diatomic, okay? So keep that in mind with the diatomics, okay? All right. So now that we've talked about what a covalent bond is and how the electrons are shared, we're going to start looking at how these molecules look. We're kind of getting ready to talk about Lewis structures, okay? So molecular compounds, we're going to start with electron dot structures, okay? That's something y'all are familiar with. We're going to start with drawing those, and then eventually we'll replace the shared electrons with dashes or lines. All right, so we have different molecules here. I kind of wanted you to see the spatial orientation, so that's why here they're represented as spheres. You can see how the atoms are kind of connected that way. So the red is the oxygen, and the 2 white on the side here for our water molecule are the hydrogens. And then here is what it looks like, its structure. Here's how they are bonded together covalently. But what we're going to do, I want you to draw the electron dot structures of each atom to discover how these covalent bonds form. So let's do that for water. And I'm just going to erase and kind of draw it in between the space filling model and the Lewis type structure. So if we have oxygen, here's what you have to do. How many valence electrons does oxygen have? You need to know that. Anybody remember?
6. Is it?
It is 6. Sorry, mid-drink. All right, so I'm going to draw those 6 valence here. 2 on top, 2 on bottom, 1 on each side. There's the 6 valence electrons for oxygen. Now, how many does hydrogen have? Because I'm going to draw hydrogen on either side. 1. Somebody held up a 1. All right. So here's our electron dot structures, okay? And as these things form bonds, the unpaired electron on each hydrogen is going to be shared with the 1 unpaired electron from oxygen. That's where the sharing occurs. So let me see if I can, well, I thought I could just grab that hydrogen. So essentially what's happening here is, I'm going to change my color here. These two electrons are going to form, these two electrons are going to form a bond, all right? So the unpaired electron from hydrogen is going to form a bond. It's going to be shared with the unpaired electron with oxygen, and then that's going to happen again with the other hydrogen. Okay, so remember, each of these dashes or these lines, this is 2 electrons. Okay, and if we were to draw it, you could draw it slightly differently. If you were to keep it all as dots, here's what it now looks like. Okay, now let's draw the electrons that hydrogen claims. Which ones does hydrogen claim? I'm going to thin down my pencil for a second. So hydrogen claims these 2, all right? And remember, hydrogen's got a full set after it's got 2. This hydrogen claims the one it shares and the one oxygen shares. And which electrons does oxygen claim? Well, it already had 6, okay? We drew 6 up here. But now it also claims the 2 that each hydrogen is sharing with it. So oxygen claims all of these. Does it have 8? Do you count up 8 in the one around the box around oxygen? Yes, you do. And so everybody's got an octet. Everybody's satisfied. This is the kind of thinking you got to quickly go through when you draw this stuff. Okay, let's think about ammonia. Ammonia is a molecule of NH3. We're going to talk about ammonia a lot from here on out in this course. So let's look at ammonia. All right, I'm going to zoom in over here. So nitrogen. If I'm going to draw the electron dot structure of nitrogen, how many valence electrons are we talking about? 5. Thank you, Jenna. So I'm going to draw 5 on nitrogen. So we've got 1, 2, 3, 4, 5. Now, one side has to have 2 electrons on it. Remember, you don't pair any electrons up until you pass 4. So one side here on nitrogen has those 2 dots because each side gets 1 dot, then we pair up the 5th one with another one. Okay, now we've got 3 hydrogens bonded to this nitrogen. So I see 3 unpaired electrons on nitrogen, right? There's 3 lone electrons. So we're going to bond those. Each hydrogen has an electron to share. And nitrogen, you can't share electrons that are paired up. You can only share electrons that are unpaired. I'm going to say that again. You cannot share electrons that are paired up. You can only share unpaired electrons. So nitrogen has 3 unpaired electrons. And if each hydrogen comes along and shares, now remember, each atom in a bond claims both of the shared electrons. So let's count, how many does nitrogen have? Well, nitrogen claims the one it's sharing plus the one hydrogen is sharing. So it has these 2 up here. That's 1, 2. Now it has 3, 4. It also owned this one and the one hydrogen sharing right here. So that's 5, 6. It also owned this one right here that I'm filling in. So that was 7. Now it also claims the one hydrogen is sharing. That's 8. So nitrogen now claims 8 electrons. That's a full octet. And then hydrogen, if we draw boxes, it claims both of those shared electrons as well. The one nitrogen is sharing plus the one it contributed to the bond. So each hydrogen also has 2, and everybody's satisfied. Okay, let's look at methane, CH4. So let's draw an electron dot structure of carbon. Here it is. Carbon it's in main group 4, so it has 4 valence electrons. There they are. What do you notice about carbon? All of the electrons are unpaired. If it has 4 valence, how many more electrons does it need to get an octet? Whoops. Crazy. Anybody ever happen to potential spam? Get a number from like Canada? Okay, sorry. The question was, how many electrons does carbon need to get 8? It has 4 and it wants 4 more. So it's going to have to share all 4 of its electrons to get another 4. So if we have a hydrogen here that has 1 electron, they're both going to share. Another hydrogen that will share its electron, another hydrogen, and another hydrogen. So here's the electron dot structures. And remember, carbon is going to claim the 4 it had plus the 4 shared by each, or 1 by each hydrogen. So that's going to be 8, the grand total of 8. And then each hydrogen will have 2 as well. So I just wanted to draw these out so you can see how that's happening, so that an octet is satisfied for every atom Okay, remember an octet means 2 for hydrogen and helium, but for every atom in a covalently bonded molecule. Questions so far on what we've done? So this phrase that we're about to fill in, I want you to know this. I want it to kind of be the jargon that you, kind of the mantra per se of this part of the content that we're talking about. Every time you share an electron, you gain an electron. That's what happens. Every time you share an electron, you gain electron. So as you're drawing Lewis structures out, as you're trying to figure out, well, how many bonds is this element going to be in a molecule? Here's the questions you ask yourself. Well, how many valence does this element have? We always started there. All right. And once you get that question answered, how many electrons does this element need to get an octet? How many valence does it already have? How many more does it need to get 8? All right. And you figure out the difference. And then this last part, the number of electrons an atom needs to achieve an octet is equal to the number of bonds it will form. So if you're wondering how many bonds will this atom form, there you go. The number of valence electrons that it needs to get 8 is equal to the number of bonds it will form in a covalently bonded molecule. All right. Questions? Confusions? Did I just lose anybody? There's some simple math involved to figure out number of bonds. Okay, and the more you practice this, the more you'll just know. It'll become second nature. You won't have to do all this little math every time. Okay, so that's kind of the review slide to recap what we've done so far. Here is a figure from your textbook that's also very helpful. This shows you how many bonds these non-metal elements will form. All right. Now, I will tell you the frustrating part with chemistry. There's lots of frustrating parts, but one of the frustrating parts is that there are exceptions. Some elements decide that they want to share more than their typical number of electrons. And those are indicated with parentheses. Okay. Anytime you see a parentheses, that's an exception. So what do we notice with phosphorus? Phosphorus typically forms 3 bonds. Why? Because it has 5 electrons. It needs 3 more to get 8. Okay. And so it typically forms 3 bonds. However, sometimes it will share all 5. If it shares all 5, for example, here's phosphorus. Let's draw its 5 valence electrons. If it shares all 5, and remember that saying, let's go up here, every time you share, you gain an electron. So what does that look like? Well, if we're going to share with hydrogens, it's going to share with 5 hydrogens. Hydrogen always has 1 to share. Now, what would this molecule look like? You would have 5 bonds to hydrogens. Okay, now this looks illegal. And for many elements, this would be totally illegal. But how many electrons does phosphorus claim here? 10. Okay, there's 2 in each line. So that exceeds the octet, exceeds 8. And you see that can happen with occasionally, like sulfur is another example. Sometimes it will share more than it should, and it will exceed the octet rule. All right, so just know that can happen. But the typical number of bonds an element will form is the one stated on this figure. And again, this is in your textbook, so you can refer to this or you can refer to it on these slides. And here's what it's showing you. Okay, it's pointing out the number of valence that these elements have is shown up here, and then the usual, we'll say usual number of covalent bonds that element will form is down below it. Okay. All right, we're going to do a poll question. I want you to look at these molecules down here, A, B, C, and D. Don't say anything. Don't shout the answers out or type them. We're going to do a poll. I want to know, are these possible correct molecules? Are these, quote, legal? So here's the poll question. Move it out of the way so that you can see the slide. And answer at your leisure. Based on what we just talked about, you need to be counting up to these elements. I've not shown you the lone pairs or anything on these. If you want to draw out the full electron dot structure, go for it. But you need to ask yourself, does every atom here, is it satisfied with the octet? We'll talk about why or why not in just a minute. If it helps you to draw in lone pairs on these things, I know you don't have a lot of experience with that. You need to ask yourself, how many valence does each of these atoms already have? How many are they going to want to share? How many electrons? Does that match the number of bonds that's typical for that element? Refer to the figure as you need to. 9 more people to vote. We're low today. Only 29. Where is everyone? I'm going to give you just another couple seconds. You last 5 people, get your answers in. 10, 9, 8, 7, 6, 5, 4, 3, 2. Calling it. Okay. So let's talk about this. Let's zoom in on the first one. Erase. We've got carbon bonded to 3 bromine atoms. Okay, we're not talking bromide here because bromide is how you name an anion, and we're not dealing with ions. We don't have cations and anions here. So carbon has 4 valence, right? 4 valence electrons. It needs 4 more, so it should form 4 bonds. And we don't see 4 bonds here. It is only bonded to 3 atoms. So is this a legal structure? Is that a real compound? No, absolutely not. Okay, let's talk about B. Carbon should have 4 bonds. It will never have anything besides 4 bonds. All right, you've got iodine and you've got chlorine bonded together here. Each of these elements already has 7 valence electrons. How did I know that? Because they're both halogens. They're both main group 7. So they have 7 electrons. They only need 1 more, each of them. So they both agree to share 1. They both should form 1 bond. That is what is typical when you look at their common number of bonds. So if you look at this, they're both sharing 1. That is legal. In fact, if we draw all the lone pairs in, I'm going to draw all the valence starting out. Here's iodine, 7 valence, chlorine, 7 valence electrons. So they both have 1 unpaired electron. Remember, you only share the unpaired. So they're going to share these right here. And that is where the bond comes in. So what you don't see again is all the lone pairs that you could draw on here to help you see that full octet, but you can certainly draw them in if you want. This is perfectly valid. All right, so that one, yes. Okay, let's talk about FH4. Can this happen? And what have people been saying? So far, most of y'all guessed no on the first one, good. Most of y'all guessed yes on the second. The third one, most of y'all said no. Okay, let's look at why. Well, fluorine, where's fluorine? It has 7 valence, it's a halogen. It only forms 1 bond typically. Why? Because it only needs to share 1 electron. Every time you share 1, you gain 1. So the fact that it has 4 bonds here, that's a no-go. And if you notice, fluorine has no parentheses underneath. There's nothing under here. There's no exceptions. So you're never going to find fluorine in 4 bonds. All right, that exceeds the octet, so no. Lastly, is this a valid structure? A sulfur bonded to 2 hydrogens. Most of y'all said yes. Let's think about that. Sulfur it's in main group 6, right underneath oxygen. Here it is. So it has 6 valence. So 2 unpaired electrons here. To get an octet, it's going to share both of those. Hydrogen, as we know, is always happy to share 1. And there's the 2 bonds that are formed. Now sulfur, both atoms claim all the shared electrons. So sulfur now claims 8. That's an octet. And remember, the common number of bonds for sulfur is 2. All right. And if you look at this structure, there's 1 and there's 2. So that's perfectly valid. Okay. All right. Questions on that? Okay. So now let's complicate things. Do you want to do that? Let's talk about multiple bonds. Sometimes atoms form not just, so far we've just been talking about single bonds. Well, sometimes atoms can share more than one electron with each other, all right? And you can form what we call multiple bonds. So let's consider scenarios where this happens. Let's look at a molecule of oxygen. We know it exists as a diatomic molecule, O2. So this is a very common molecule. We depend on it every second of every day. We've got 6 valence in each atom, right? So both of them want to have 8 electrons. So if they both share, starting out sharing 1 electron each, what happens? If we share 1 electron each, well, we had 6 valence. Now, how many does each oxygen have? Let's look at this oxygen over here on the left. It's got 1, 2, 3, 4, 5, and then there's 2 here, so that's 6, 7. So now each oxygen has 7 electrons, 7 valence. It's not satisfied with it just sharing 1. Okay, so this is not stable. So it can't stop here. They both still have 1 unpaired electron. So they're like, you know what? You want to share another one? Yeah, sure, let's do it. Me too. So now if they both share again, that looks like a double bond. That's what happens. Now, how many do they still own? They have not shared the 2 unpaired on top and bottom. These are not shared, okay? So they still own 2 on top and 2 on bottom each. And remember, they both claim all the shared electrons. So what we've got here, when we both decide to share 2, this is 2 electrons. Down here, this is 2 electrons. And they both claim all of those. So now they have 4 unshared electrons that they own, and they claim the 4 shared electrons. That adds up to 8. So now each oxygen has 8 electrons, and this is stable. So oxygen is a molecule that is only stable when it shares 2 each. It's only stable with a double bond. Okay? Let's talk about nitrogen. What happens with nitrogen? Nitrogen has 5 valence. So how many does it need to get an octet? It needs 3 more. So it's got to share 3 electrons. It's got to form 3 bonds. So if it only shares 1 starting out, okay, then what it still has, it started out with 5 valence, and you see those 5 over here. If they both share 1, they own 4 that they've not shared. There's the 4, and then they're each sharing 1 here in the middle. So now how many does each nitrogen claim to have? 1, 2, 3, 4, and then there's 5 and 6 here. So now each nitrogen has 6 valence electrons, and that's not stable. Can't stop there. Well, what if they share again? That looks like a double bond. Okay. So there's 2 electrons in that top bond, 2 in the bottom. Remember, each nitrogen started out with 5, and you see that over here. They're both sharing 2, so they still own 3. Here's the 3 that they have not shared. Now, how many does each nitrogen claim to have? There's 4 shared in those bonds, and they each own 3, so that adds up to 7. So now each nitrogen has 7 valence electrons. And this is still not stable. This is not an octet. So they can't stop there. So they have to share 3. That's the only time nitrogen is satisfied. And then they have 2 electrons that they're not sharing. Okay? So there's 6 shared. And remember, each nitrogen claims all 6 of those. plus it has 2 of its own. 6 shared, 2 that it owns, so that adds up to 8. All right, and this is stable. Questions on multiple bonds? Okay. Now you have to consider elements in the same groups as nitrogen and oxygen. So sulfur, phosphorus, when those atoms are bonded to each other, so 2 atoms of sulfur bonded together, 2 atoms of phosphorus bonded together, they're going to behave the same way. So there's other elements besides oxygen and nitrogen that will form multiple bonds like this. If they're in the same group as oxygen and nitrogen, when they bond together, 2 identical atoms, they'll form multiple bonds. Okay. All right. We're now going to get into, we've been talking about all this covalent bond stuff, counting the octet, sharing electrons. Lewis structures are going to help us visualize this and help us learn this to the kind of the final degree that we need to go to. So what the heck is a Lewis structure? Lewis structures are a way to see the way atoms are, I guess I'll say visualize the way atoms are bonded. Okay, I want you to see the spatial orientation. How are which atoms in the middle, which ones on the outside? That's what I'm talking about. How are these atoms arranged together? Okay, so they're essentially extensions of electron dot structure. We've kind of seen that. So here, SH2, this is an example so far of what we would have talked about. This is a formula for this molecule. It's just the shorthand. We've written the electron or the element symbols, and we've written the subscripts. That's a formula for a compound. Now we want to see which atoms in the middle, which one's on the outside. Now we're going to draw the Lewis structure to see that. So is a hydrogen in the middle or is the sulfur in the middle? So the Lewis structure is how we tell how the atoms are arranged. Okay, and Lewis structures are different than other types of formulas because you can also see what we call our lone pairs of electrons. We'll draw in the bonds as lines or dashes, and we'll draw in the lone pairs. And notice when I say pair, what does that indicate? That indicates 2 electrons, okay? So a lone pair is never just one single electron, it's a pair. It's 2, remember that. Okay, with water here, we've already actually drawn this out, but we see the electron dot structures, and then we just draw the ones that are shared as the bonds, okay? And it shows us how the atoms are arranged within the molecule, all right? And then down here, this figure is from your textbook as well. It's just pointing out the fact that we have to draw in lone pairs on Lewis dot structures, all right? Some atoms will have lone pairs, some will not. Carbon, look at this over here. Carbon will never, ever, ever, ever have lone pairs. Okay, now I'm saying this and I exaggerated the never, ever, ever part, and I guarantee you on exam 2, somebody is going to draw a carbon with lone pairs on it. Okay, somebody is going to do it. Don't be that person. Please do not ever put lone pair. I'm making a big deal out about this. You will automatically lose points if I ever see a lone pair on carbon. Don't do it, okay? You please draw me something else crazy that doesn't make sense, but don't put lone pairs on your carbon or I will laugh at you. I won't blast you in front of everybody, but don't do that. All right, we're going to learn there's 5 rules for drawing Lewis structures. That'll help guide us on how we get the structure correct. But real quick, I'm just going to address carbon, nitrogen, oxygen, halogens, and hydrogen. Okay, these types of elements, and then any element that's in the same group as these, here's how they should look. We're going to draw what each atom would look like in a molecule. Carbon will always have 4 bonds, but it can look different ways. It can have 4 single bonds. So that looks like this, 1, 2, 3, 4. It can have 3 single, I'm going to abbreviate, 3 single and 1 DB, 1 double bond. What does that look like? Carbon with, 2 single. My math is not correct there. Only 2 single and then a double. That adds up to 4. And then it could have one single bond and one, I'll put TB for triple bond. So you can have a carbon that looks like this. These are all valid. You'll never see a quadruple bond. Triple is as high as it goes. Okay? So you can have a carbon with 4 single bonds, carbon with 2 single bonds and a double bond, a carbon with 1 single bond and a triple bond. That adds up to 4, right? Carbon can always look that way. Notice there's no lone pairs anywhere on a carbon. Okay, nitrogen. Nitrogen should always have 3 bonds, but it can look different ways. You can have 3 single bonds. So you can have a nitrogen that looks like this, and then it will have a lone pair on it. Nitrogen usually always has a lone pair. You can have 1 single bond and then 1 DB, double bond. What does that look like? You can have a nitrogen that looks like there's the single bond, there's a double bond. We're still going to give nitrogen a lone pair. Then you can also have a nitrogen with 1 triple. We've already seen that actually, nitrogen bonded to itself, 1 triple bond. That is a nitrogen that looks like this. And remember, it has a lone pair. Okay, so I'm just drawing out the different ways these atoms can look, and elements in the same group. So another element that's in the same group as nitrogen is phosphorus. So guess what? We could substitute that in for a P, because phosphorus can look this way as well. Oxygen should only have 2 bonds. How can that look? You can have 2 single. That is an oxygen that looks like this. Can carbon have, oh, Abby, thank you. Forgot one for carbon. I just got a question in the chat. Carbon, I forgot one way carbon can look. It can have 2 double bonds. Thank you. It can look like this. Yes, it can. That adds up to 4 as well. So there's 4 different arrangements for carbon. All right, back over here to oxygen. We can have 2 single bonds, and then oxygen should have 2 lone pairs. Or you can have 1 double bond. And that is like this. And then oxygen still gets 2 lone pairs. Sulfur is in the same group as oxygen, so sulfur can look this way as well. Okay, halogens. Halogens, this is fluorine, chlorine, bromine, iodine. 1 bond. Okay, we know halogens. I'm going to put an X here. It can be F, Cl, Br, or I. They have, here's what they look like usually, 7 valence. But they are going to share that 1 unpaired, and you'll get a single bond. That's the only way it can look. Okay, and then lastly, hydrogen, very simple. Hydrogen has no lone pairs. No lone pairs. Okay, so just like carbon, don't ever put lone pairs on a carbon. Don't ever put lone pairs on a hydrogen. Okay, that's what hydrogen looks. So here's just some examples. I put some molecules down here on the bottom for you to see as we begin getting bigger and bigger structures. If you look at ethane here, we've got a lot of atoms, but everybody's abiding by their rules. Carbon, this carbon right here, has 4 single bonds. 1, 2, 3, 4. This carbon over here on the right, 4 single bonds as well, and hydrogen always has 1 bond. Look at this one. This carbon in acetaldehyde has 4 single bonds. Hydrogen each has 1 bond. The oxygen here, we said it can have a double bond, and it does, and then 2 lone pairs. The carbon, it's still got 4 bonds. It just looks different. It's got a double bond and 2 single, okay? So I just wanted to kind of get your brain wrapped around this. There's different ways things can look, but it's all the same thing. They all end up with the same number of bonds. All right, so here's the 5 rules that I mentioned for drawing Lewis structures. Let's fill this in really quick. Find the total number of valence electrons for all the atoms in the molecule or the ion. Find the total number of valence electrons. So you're going to figure out how many carbons do I have? Each carbon has 4 valence. Multiply that out. How many hydrogens do I have? Each hydrogen has 1 valence. You'll add all that up. We'll do some practice problems. That's rule number 1. get the total number of valence. And then 2, you're going to draw a line, whoops, between each pair of connected atoms. And that line represents the 2 electrons in the bond, the covalent bond. So add up the total number of valence, start connecting the atoms that look like they could be connected together. Again, we'll practice how to do this. 3, use the remaining electrons and add lone pairs so that each atom that is connected to the central atom, so we're talking about the exterior atoms now, gets an octet. Notice the exception here is hydrogen will never get lone pairs. Once hydrogen shares and it has a single bond, it's done. But other atoms, nitrogen, oxygen, sulfur, phosphorus, you can start putting lone pairs on them until they get an octet. If you still have electrons left over, you haven't reached your total that you found in rule number 1, place any remaining electrons as lone pairs on the central atom. And what do I mean when I say a central atom? Okay, a central atom, if we're looking at ethane right here, the carbons are central atoms. They're the ones that are not on the exterior, they're in the middle. Okay, rule number 5. If the central atom does not yet have an octet after all the electrons have been assigned, what do? You take a lone pair from a neighboring atom and you form a multiple bond to the central atom. We're going to do some examples. Okay, that's a lot of information that we just filled out. Let's do some examples so that you see how these play out. Lewis structure, and look, I have lots of examples here. I have 6. We're not going to get to all 6 today. I'm going to do probably these first 3, and then the 4, 5, and 6 you can try on your own, because after Lewis structures, we need to talk about condensed structures and try to get to some geometry today, and we have limited time. So first rule is we're going to add up the total number of valence. Let's do this for number 1, C3H8O. So how do we do this? In this molecule, we have 3 carbons. We know carbon has 4 valence. We know hydrogen has 1 valence. And how many does oxygen have? It has 6 valence electrons. How do I know this? Well, you look at what main group it's in, okay? And the main group matches the number of valence. So for carbon, you'll do 4. There's 4 valence for every carbon, and we have 3 of them. So that adds up to 12 valence electrons. Hydrogen, you have 1 hydrogen, and each one, or sorry, you have 8 hydrogens. All right, each one has 8 valence. Whoa, I'm getting mixed up. I have 8 hydrogens, each one has 1 valence. So that's 8 total. Oxygen, I have 1 oxygen in my structure. That 1 oxygen has 6 valence electrons. So now let's add all this up. We should have 26 in our structure total. 26 valence electrons. Okay, so here's the deal. I want you to try to draw this out. Different people are going to have different structures. There's different ways you can piece this together. Sometimes there is more than one valid structure for a molecule. So here's what I know. Can you ever have hydrogen be a central atom? No, it can never have more than 1 bond. And a central atom has more than 1 thing bonded to it. So I'm not going to put hydrogen in central. I'm going to start connecting carbons because carbons are always good central atoms. So here's what I'm going to do. I'm just taking a stab here. I'm just going to connect these 3 carbons. Okay, now I'm just going to look up here at ethane. Very commonly, you see all these hydrogens branched off of the carbons. That's a very common thing. So I'm just going to start throwing hydrogens on my carbons until we get 8. So this carbon was already involved in 1 bond to another carbon, so it can get 3 more bonds. Now this carbon that we just surrounded has 4 single bonds. That's as many as it can have. These hydrogens all have 1 bond, so everybody's satisfied with an octet. Remember, each bond, each line represents 2 electrons. You can add up all those electrons for carbon. Okay, we've got 3 hydrogens. We still have 5 more hydrogens to account for, so let's just keep putting them on carbons until we get 8. So now we have 1, 2, 3, 4, 5 Okay, we need 8. Can I do this? Can I do that? Is that okay, what I just did? Abby's shaking her head. No. Olivia says no. Why can't I do this? What's wrong? Anybody know why this is not okay? We still have an oxygen to account for, but I have no bonds left on my carbons. I don't have anywhere to put that oxygen. So let's back up. I'm just going to erase a hydrogen here. What if I put an oxygen there instead? I'm just guessing here. Well, we're not done. We only have 7 hydrogens accounted for. We need 1 more hydrogen. Okay, and look, remember oxygen has to have 2 bonds. Remember up here? Oxygen can have either 2 single bonds or a double bond. And it's got to have 2 lone pairs. The oxygen I've drawn only has 1 bond. So we need another bond. And guess what? We have another atom. We have a hydrogen. Why don't we just bond it to that hydrogen? Okay. And then oxygen should have, how many electrons does this oxygen claim right now? Remember, it needs an octet. It only claims 4, not 2. It's in 2 bonds, and each bond is 2 electrons. So it claims 4 right now. It needs to have 8, and those other 4 come in through lone pairs. Now, listen, if this is all way over your head right now and you're so confused and so lost, don't worry, we're going to practice this. But remember, if you follow these rules, you'll get the right structure. So what we did is we did number 1, we added up the total, we started drawing lines connecting things. All right, we used the remaining electrons, we put lone pairs on that oxygen. Here we're at step number 4. Do we have any remaining electrons or have we used them all? Let's count them up. If you remember that each bond represents 2 electrons, let's count them up. So this bond is 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Here's 2 more, so that's 22. Here's 2 more, that's 24. And then this one right here makes 26. That's how many we're supposed to have, right? So we're done. We don't have to do rules 4 and 5 because our structure is done. Everybody is satisfied. Everybody has an octet. So there you go. You could have drawn this other ways. You could have bonded an oxygen between 2 carbon atoms. There's multiple ways you could have drawn this. Questions on that? Okay, let's start number 2. Go ahead and add up the total valence. I'm going to start doing this as well. Did y'all get 26 again? Okay. All right, so as you begin to piece this together, remember, I'm going to scroll back up for a second. We've got carbons, hydrogens, we've got a halogen here, fluorine, we've got oxygen. They need to match one of the ways we drew them out up here, okay? So fluorine should only have 1 bond. All the hydrogens should only have 1 bond. Make sure they match what we've drawn up here. So again, I like to start out oftentimes just go ahead and connect my carbons. All right. Then I'm just going to throw the hydrogens on the carbons again like we did previously until this carbon has 4 bonds. Now let's move to the next carbon. This is 4 hydrogens. We only have 5 hydrogens to account for. So there's all 5. Now what could I do? I still have two atoms that I have not drawn in my structure, a fluorine and an oxygen. Can I put fluorine right here? Is that okay or no? Y'all are shaking your head no. Why?
The oxygen needs to be in there.
It does. And remember, fluorine, if we looked up at that slide earlier, fluorine has 3 lone pairs on it and a single bond. We have no place to put the oxygen now if we draw the fluorine right there. So I cannot put fluorine there. Fluorine is always an exterior atom, just like hydrogen. Oxygen, however, if we draw oxygen right there, oxygen has room for another bond. It should have 2 bonds, whether it's a double bond or a single bond. Could I put a double bond right there? Is that okay to do? No, because I don't have spot for my fluorine now. Oxygen is satisfied. And look, we violated that carbon. That carbon is highly offended. We just totally violated that carbon. We gave it 5 bonds. We cannot do that. Okay? Carbon can only have 4 bonds. Don't ever give it 5. So we can put that fluorine on the other side of the oxygen. It has 1 bond. It has 3 lone pairs. If you remember from how we drew it up above. Is this valid? I don't know. Let's count up our electrons and see if we have 26. Remember, every line represents 2 electrons. So 2, 4, 6, 8, 10, 12, 14. Here's 2 more. That's 16. 2 more. That's 18, 20, and then 22, 24, 26. And we were supposed to have 26 in our structure. We do. We're done. We didn't have any multiple bonds here. Again, you could have drawn this different ways. So if you came up with another structure that meets all the requirements, then it's probably a valid structure. Okay, let's do number 3, and then we're going to move on. Sorry, it's some water. Okay, NCl3. So let's add up the total number of valence. Nitrogen, we have 1 nitrogen, and that has 5 electrons, so that equals 5. Chlorine, we have 3 of them, so 3. Each one has 7 valence. So 3 times 7 is 21. Guess what? 26 again. Okay, this one should be a little easier. There are fewer atoms here, but you need to decide which element is my central atom, which one is my exterior atom. Chlorine is a halogen, and remember we said halogens always look like this. 1 bond, 3 lone pairs. Nitrogen has 5 valence electrons. How many more does it need to get an octet? It needs 3 more. So every time it shares 1, it gains 1. Every time you share 1, you form a bond. So nitrogen, remember, it can have 3 single bonds, a single and a double, or a triple bond. Here it's going to have 3 single bonds because it's bonded to 3 chlorine atoms. Now, let's talk about nitrogen really quick. If we're following through the rules here, we did number 1, we added up the total valence. We did number 2, we drew a line to connect our atoms. Now number 3, using the remaining electrons, we're going to add lone pairs to the atoms that are connected to the central. So that's the chlorines. So let's just start putting lone pairs on the chlorines until everybody's satisfied. Now chlorine has an octet. It's satisfied. That chlorine also has an octet. Now they all have octets. Okay, have we used all of our electrons? Let's check. Okay, because it says 4 says place any remaining. Well, do we on the central atom? Do we have any remaining? Well, let's count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We're supposed to have 26. So we've got 2 electrons missing. And rule number 4 says now place any remaining electrons as a lone pair on the central atom. So we're going to go back to nitrogen, and I'm going to put a lone pair on nitrogen. And that completes our 26. So what you end up with is this. And then everybody gets an octet. Okay. Questions there? Okay. Well, that's kind of it for Lewis structures. You're not done studying Lewis structures. Like if you were done and try to go take the exam on Lewis structures, that would not go well with you. So practice these. How do you get better at these? You practice them. So that's why I have some examples here. At the back of chapter 4 in the textbook, there's so many problems. And as we get closer to exam 2, I'll post textbook problems for you to practice Lewis structures. Okay, the lab that we have due next week, I think is the one on Lewis structures, so we'll practice this even further. Okay, let's talk about condensed structures. This is another way to represent, oh gosh, we only have 5 minutes left. I wanted to get through all of this. I'm going to talk about this for just a minute or two. We're not going to get through it all, so we'll pick up with this on Tuesday. I'm just going to explain what it is and give you an example, and then we'll be done for the day. It's just a way to represent the molecule it's kind of a shorthand notation. It's different from a Lewis structure, but it's still, you read condensed structures and you can still see how the atoms are connected, same way you would for Lewis structures. So again, if we start out with a molecular formula, the formula just tells us how many carbons and how many hydrogens are in ethane here. But we have no idea how they're connected. Okay, well, the condensed structure is going to teach us how they're connected. And here's how this works. Carbon and oxygen and nitrogen, things like that, those can be central atoms. Hydrogen, we have seen that it can never be a central atom. So if you start with this first carbon right here, anything following that carbon until you get to the next central atom is attached to that carbon. So all these 3 hydrogens, these are attached to the preceding carbon. Okay, and then guess what? We have our next central atom, carbon. Carbon can be a central atom. So these carbons are bonded, and these 3 hydrogens are attached to that carbon. Okay, so that's how you read these structures. In fact, let's look at a very exaggerated example here. We have C18 or C8H18O. This is a huge molecule. We could never guess in our wildest dreams how these atoms are connected, right? But if we have the condensed structure, and this is very long and overwhelming, I know, but we can see how it's connected. All of these hydrogens, they're attached to the preceding carbon. Okay, it's written as little groups here. And then these carbons are what we call the main chain. And they are chained together. And then anything between those carbons is branched off of the main chain. So if we start drawing this out, a carbon, this is carbon number 1, this is carbon number 1. We've got 3 hydrogens here that we're going to branch off of carbon number 1. And then we said carbon number 1 is attached to carbon number 2. So we would continue the main chain. Carbon number 2, guess what? It has 2 hydrogens attached to it. So we're going to branch those off of carbon number 2. Carbon number 2 is main chained to carbon number 3. And then so on and so forth. You see this pattern continues for quite a while. We have 1, 2, 3, 4, 5, 6, 7, 8 carbons. That's carbon 8. So you would just keep going. 1, 2, 3, 4, 5, 6, 7, 8. Okay. And then you would branch off all your hydrogens off of those carbons. Now in the end, we have an OH. Oxygen can be a central atom. It can have more than one bond. So we're going to bond this last carbon to that oxygen. And that oxygen has a hydrogen connected to it. And at the end, it doesn't matter if you go straight out or up or down, because it ends the molecule. So I could bond the hydrogen here. I could branch it straight out to the right. I could branch it up. It doesn't matter. And then remember, oxygen should always have 2 lone pairs. So this is an example of a condensed structure. We're not drawing out all the bonds. We're not drawing out all the lines, but you can still read the condensed structure and imagine this, how they're connected. Okay, so the condensed structure helps you imagine all the branched atoms and how they're connected. All right. So guess what we have? A lot of practice problems. We are not going to get through all of these. We're just going to do one. Okay. So I'm going to skip over A, and I want to do E. We're going to spend a minute here. We have 2 minutes left. I know. We're going to do E really quick because I want to explain one thing that I have yet to explain. You see parentheses here. What do those mean? Oxygen could be part of the main chain. There's several atoms that could be on the main chain. Carbon, nitrogen, oxygen. If it can have more than one bond, it could be part of the main chain. So how do we know if something is a part of the main chain or if it's branched off of the main chain? That's what these parentheses are telling us, okay? Anything in parentheses is branched off of the main chain, all right? So parentheses are also used to further abbreviate condensed structures. Anything in parentheses, this means it is branched off of the main chain. So really quick, let's draw the structure. Start with a carbon here, and we're going to branch 3 hydrogens off of that carbon. So here's what that looks like. Boom, boom, boom. Now this main chain carbon is connected to the next central atom. So we're just going to continue. We kind of read these left to right. Okay, and then you see something in parentheses. You see an oxygen, it is branched off of the main chain. Now what are the rules for oxygen? Oxygen can either have 2 single bonds or a double bond. Well, here, oxygen, there's nothing else in this parentheses, so that oxygen has nothing else bonded to it. The only atom it's bonded to is that carbon. So what that means, what I'm asking here is I'm going to bond the oxygen. It doesn't matter if I go up or down. It doesn't matter. I could have drawn it down here, but I didn't. It doesn't matter. It's bonded to that carbon. Can I draw it with a single bond, or does it need to have a double bond? It has to have a double bond. And it gets 2 lone pairs. Does this oxygen now have an octet? Yes, it does. Okay, so that gets us to this oxygen. Now this carbon is bonded to the next main chain carbon. So we're going to continue. And now look at this carbon right here. How many bonds does that carbon, this carbon number 2, have? It's got 4, right? So are we legal? We are. A double bond and 2 singles, that adds up to 4. This third carbon that we've just drawn has 2 hydrogens. We're going to branch those hydrogens, one here and one here. Sorry guys, we're almost done. Hang with me. Now we are on this next group, CH2 bonded to another CH2 group. Those hydrogens are branched off that carbon. We get to our next to last carbon. And look, same thing as before. We have an oxygen in parentheses. So I'm going to branch this one down just for the fun of it. And doesn't matter up or down. So that oxygen looks like the same oxygen as earlier because it's only bonded to that carbon. And then this oxygen, however, is not in parentheses. So what does that mean? That means it's not branched off of the main chain. It is part of the main chain. Is this oxygen going to have a double bond? Well, it is bonded to that carbon, but then we see this oxygen is also bonded to the last carbon. So it cannot have a double bond. It's 2 single bonds. We still put 2 lone pairs on oxygen every time. And then we have a CH3 group. Okay. So last thing I'm going to do is I'm going to draw the groups. That's a group. This was its own group. This is a group. You read these in groups, okay? All right, that's it for today. We'll do more condensed structures on Tuesday. I know this is probably, I had a poll. If you want to stick around and answer my poll, if you want to go, go. I'm past time. But I wanted to ask you guys, review. Here's some review questions. There's just 3 review questions. So if you want to stick around and answer these, thank you. If you need to go, if you got somewhere to be, go. Review question 1. The number of valence electrons an element already has is equal to the number of bonds it will form in a molecule. True or false? Number 2, how many bonds will silicon, Si, form in a covalently bonded molecule? You need to see what group is it in. How many valence does it have? How many electrons does it need to get 8? Then number 3, I pretty clearly comprehended what percent of the material today. Thank y'all for joining. Sorry that we went over. We still got people voting. I'll give it another 20 seconds. Oh, 11 of 12. We're basically there. End poll. If you said false on number 1, you got it right, okay? It's not the number of valence electrons that an element already has, it's the number that it needs. So if it has 5, then it needs 3 more. It's going to form 3 bonds. So the number of electrons that an atom needs to get 8, that's how many bonds it will form, not the number it already has. So that was false. Silicon. Silicon is in main group 4, so it has 4 valence. That means it needs 4 more valence. So it will form 4 bonds. Remember, the number that it needs is equal to the number of bonds it will form. And most, okay, I can handle that. Most of y'all said you got about 75% of it. All right, guys. That's all I have. Any questions?